works.
So
this is Vasilis.
Yes. So hello to everyone. That's enough. I'm Vasilis. So yeah, I'm Vasilis. I'm a third-year ITAMP fellow. I've been 3 years here, and first of all, I want to thank Hossein that brought me here. I mean, as under his directorship, and I have been working with him. It has been a great pleasure, and also Jacqueline and Hossein for organizing this event. It's amazing, and it's really great to be part of such a reunion. So today I will be talking to you about very similar topics like Johannes, and this, to some extent is a blessing to come after his presentation, but also a curse, because it was really great to be introducing why this is interesting, like to look about cavities, but he said that all single mode models are wrong and misleading, so this is a wrong and misleading talk, okay? So the work that I have been doing at ITAMP is like motivated by what Johannes already introduced, like this transition in cavity QED going from weak coupling to the strong coupling. And this is, of course, because of experimentalists that they managed to really build these novel electromagnetic environments in cavities. And, of course, when they are in resonance and so on, they see, due to strong coupling, the formation of these hybrid quasi-particles between light and matter. And this polariton formation has been shown that it leads to modifications of material properties. And two particular examples that are now sort of emerging in this sort of modern era of cavity QED, where we do not now have only atoms being coupled to cavities, but actually also 2D materials and molecular ensembles. And again, experimentalists is especially on the right-hand side that took really the lead, and Thomas Ebensen pioneered this field. And what they observed, these guys, is that you can modify like large ensembles of molecules in solution when you couple them resonantly to terahertz cavities. And also in the material side, the FISE group has been doing really exciting experiments with quantum Hall systems when they have been now observing modifications of transport. There have been, of course, a lot of theory proposals on this. And this field is sort of growing, but on an experiment, as Johannes also said, it's still a little bit limited. So theory on this side has been doing most of the work. And my outline for today is I will try to present to you I've been a bit ambitious with trying to present two talks. And what connects these two, on the one hand side, we have cavity quantum Hall systems. On the other side, we have cold ions in harmonic traps, is that both such systems are actually harmonic. And that's why I grouped them together. And on the first part, we will look into how transport properties of quantum Hall systems get modified due to polariton formation, and look into potential mechanisms for observed very strong modifications of quantum Hall transport. And on the second part, we will try to look now again into collective polariton states of such charged cold ions in traps, how photon correlations build up, modifications of ground state properties, and some cavity-mediated interactions in the single mode case, and also some recent preliminary results with Ilya Tuturnikov on dynamics of such systems. So let me start with the first part, which is like a collaboration both with the people at ETH, the group of Jerome Feist, the Rubio group, and also Ji Wang from Temple University. So what has been going on in this field is, as said, due to the Feist group, so like somewhat 10 years ago, what these people did is to take essentially gallium arsenide samples, put them in these complementary split ring resonators, and then put the whole system into very strong magnetic fields. And here on this linear dispersion, this linear excitation, it would be just the bare matter excitation of the Landau levels, the cyclotron transition. This would be just the flat transition of the split ring resonator, which provides you terahertz modes. And what they observed when they put them together is these very large vacuum Rabi splittings, which, as Johannes said, is in the ultra-strong coupling regime. So this avoided crossing here between the upper and the lower polariton is comparable to the bare matter and light excitations in the system. And since then, more groups have been performing similar experiments in these platforms. And again, the Feist group, now they went a step further and not just do simple transmission spectroscopy, but now actually doing quantum transport of such systems in these terahertz resonators. So let me try to at least explain a couple of things on this plot, although it's extremely complicated to understand what is going on. So the black lines that you see here, this is the longitude, this is the transverse, this is the transverse resistivity. Oh, why is this happening? So this is the transverse resistivity in the outside of the cavity, and the black line here, this is the longitudinal resistivity outside the cavity. These are the beautiful topologically protected quantum Hall plateaus of the quantum Hall effect, and where you have a plateau, you expect to have zero resistance. And now the blue lines is what happens when you put the system in the cavity, and now hell breaks loose, and you see that here you're no longer having a zero resistivity state. This is finite. Some of the plateaus have been shifted. The ones with the arrows, which are at the odd fieldings, they are said that they were completely gone. And this whole thing was coined as the breakdown of topological protection by vacuum cavity fields. And of course, this poses many challenges, because this should not be happening, because these plateaus are topologically protected by any type of local perturbation in the system. This includes essentially all type of electrostatic interactions you can think of, and also by gauge invariance and Laughlin's flux insertion argument. This should not be happening again. So it's really a question how this is possible, and what I will try to show you today is just a first step towards understanding what might be causing this. So some kind of fundamental simple model which can tell us what kind of mechanisms can play out to see any deviations from this quantization of the Hall plateaus, which should not be violated by anything. So the system that we will consider is essentially free electrons in a 2D plane in a strong magnetic field and between some mirrors, which give us a quantized mode of a cavity. Without the cavity, this would just be the standard Landau levels. And the Hamiltonian we will be using is just a simple minimal coupling Hamiltonian. So these are the momenta of the particles of the electrons. We have n of these guys because it's a full electron liquid. Then we have the homogeneous magnetic field. So this one here, which produces the Landau levels. And then this is the quantized field of the cavity in the single mode approximation. And the polarization now is taken to be along the polarization of the external field, such that these two guys see each other and couple. And this is the energy of the quantized mode of the cavity, and this is the Coulomb interaction between the electrons. And of course, this is an n-particle system, so it looks difficult to make progress, but actually it's very simple because the system is homogeneous and harmonic. So what this means is that I can go now into the center of mass of the system, so I define the collective position of all the charges, and these are the interparticle distances. And then what you find is that the Hamiltonian is separable between the center of mass part and the interparticle essentially degrees of freedom. But the cavity field, the A hat, only couples to the center of mass. And this is essentially what allows us now to go into a reduced way of describing this, so we can essentially integrate out the interparticle correlations because they do not affect the photons, so they do not change at all the light-matter correlations in the system. So all light-matter phenomena happen in the center of mass Hamiltonian. And what you have now, this is the momentum of the center of mass. It, of course, experiences a magnetic field. It couples to the cavity field, but it couples via an enhanced coupling. So from just a single charge, we have a square root n enhancement because of this collectively coupled electron liquid. And these are two harmonic modes. So we know how to solve such systems. We just do a Bogolyubov transformation, and then we can actually find the polariton modes. So these are the hybrid modes, and they depend, of course, on the cavity frequency, the photon mode here. This is the cyclotron frequency, the one which of the Landau levels. And we have this diamagnetic frequency omega d, which essentially comes from the A squared term, which depends on the full electron density that we have in the system. So now we can plot these guys, and we see what also Johannes explained. You get this large avoided crossing. So this is the upper polariton, and this is the lower polariton, and this is the point of avoided crossing, and this is densities and effective masses from the experiment. And here we have something like 1/3 of a normalized vacuum Rabi splitting. And if you increase the density, then you see that this becomes even larger. So we have indeed this square root n with the density enhancement of the vacuum Rabi splitting, and we are indeed in this ultra strong coupling regime, as also Johannes defined it, because this ratio of the avoided crossing is it's larger than 10%. So now what is more interesting is not just to look into these polaritons, but to do transport on them. So now what we'll be doing, we apply an external time-dependent electric field, and we look into the current response of the system. So we do Kubo linear response formalism for the optical conductivity, and you have to compute the current response function. And once you do this such a computation for the hybrid system, and now you compute the longitudinal optical response, then indeed you see, so similar to a transmission type of spectroscopical experiment, you see indeed an upper polariton mode and the lower polariton mode. It's what you get, what you expect. And you get this large vacuum Rabi splitting, which is at, this is the resonant point between the Landau level and the cavity, which is around 0.3 Tesla. And this is a thumbs up in the sense, okay, you get what you expect. But now a little bit more what you can learn from this plot is that we have a gap reduction here. So this is the cyclotron gap, and this is the lower Landau polariton gap, and it's smaller. And topology crucially depends on gaps. So if you suppress a gap, then you expect that maybe topological protection is somehow weakened. So let's see whether this is true. So first now we look at conduction properties at 0 temperature. And now we consider the DC resistivities, the DC conductivities in the system. So we have T equals 0, and the system is closed, no leakage, no dissipation, so the polaritons have an infinite lifetime. And what you find is what I explained to you in the beginning, that in this case, you get what topological protection tells you. So the whole conductance is perfectly quantized, depends on only these two fundamental constants of nature, and the longitudinal conductance is 0. So unfortunately, at T equals 0 and with an infinite polariton lifetime, you just go back to these theorems of Thouless and Laughlin and so on, that the system is topologically protected, and you cannot, no matter how strong is the coupling or whatsoever, you always get this. So that's disappointing. So what I have told you is that we have this corner of topological protection, but now we want to add something which can change that. And we want to look now what happens as we go from infinite polariton lifetime into some finite one, and also what happens when you increase the temperature in the system. So let's look what happens with the lifetime. So now what we do in our Kubo transport formalism, we add a finite broadening of 5 gigahertz. And now things change a little bit. So here what I show you is the value, is the whole conductance inside the cavity and its deviation at a particular plateau. So we are at plateau equals 4 at 2 Tesla. And now as a function of the cavity frequency, we see that there is indeed a deviation from the exact quantization. So things now start to depend on the cavity parameters once you include some finite polariton lifetime. And if we do it for a second plateau at 1 Tesla, which means you are at filling factor 8, now you see that the deviation is even larger. Why? The reason is because the B field is weaker, so the cavity field can compete more, and it can compete more with the external magnetic field. So what this tells you is that it is not just ultra-strong coupling that can give you any kind of deviation from topological protection in such a system, but is the combination with some finite polariton lifetime that can do something to this system. So, and another important effect that shows up in this experiment is that there is a difference, a crucial difference between odd and even plateaus. I think I briefly mentioned it. So the odd plateaus seem to be much more affected in the Feist experiments. And the odd plateaus in the quantum Hall effect are because of the spin degree of freedoms on the Zeeman splitting, while the even are because of the Landau levels or the orbital motion. And in the experiment, the Zeeman gap is found to be 1/5 of the cyclotron gap. And because we were a bit lazy, what we thought to do is like, okay, let's think a little bit as also people thought in terms of composite fermions. So let's describe the odd plateaus as Landau levels, but with an effective magnetic field, which is 1/5 of the actual B field, such that we actually reproduce the Zeeman gap. And then we run a calculation for the parameters in the experiment. And now we look how much the longitudinal conductance deviates from 0. So this is plateau nu equals 8 at 1 Tesla in the even quantum Hall plateau. And the corresponding odd now plateau, which would have a 0.2 Tesla, it gives you something like an order of magnitude larger effect. So this sort of, at least qualitatively, tells you indeed that there should be a big difference between odd and even plateaus, just because essentially the gaps are really very different. So this sort of made us kind of happy that we can get at least qualitatively what is going on with this difference between odd and even. And now we want to see what happens as we crank up temperature, because in principle these experiments, they are at low temperatures, something like 50 to 100 millikelvin, cold for condensed matter people, not for ultra cold people, okay? So and now we want to see how thermal activation of the transport plays out in this hybrid polariton system. So now what we do, before I go into the hybrid case, let me tell you how longitudinal transport activates with temperature in a quantum Hall system. So it goes exponentially with a gap. So as you increase temperature, you should be seeing longitudinal transport to go exponentially, and delta here is the gap in the system, and in an integer quantum Hall system, the gap is the cyclotron gap. But as we saw before, here now we have a new gap, which is the lower polariton. So this implies that something, if this law is correct, then something should be different now in the thermal activation. And this is what we did now. We did the actual calculations using the Kubo transport. And this is for the case where the cavity frequency is like 0.14 of terahertz. This is the experimental case, and this is the densities experiment. And we see indeed that it activates exponentially. And now we play with the parameters in the system. So we make now the cavity frequency smaller. What this does is that it essentially reduces the value of the lower polariton. And that's why you see then that the activation becomes faster with temperature, because the gap is smaller. And if you now increase the particle density, which increases the vacuum Rabi splitting, so again this reduces the lower polariton gap, then you see that the activation becomes even faster, because again your gap has been again suppressed. So what this plot essentially tells you is that indeed the cavity modifies the thermal activation gap and enhances the thermal effects in the system. So this sort of indeed corroborates this idea that topological protection is weakened because we have this reduction of the gap from the cyclotron to the lower polariton. So going back into this sort of kind of phase diagram, indeed we have this corner of topological protection, which you just go back to these theorems of Thouless and Laughlin. But there is actually this whole realm here where quantum Hall transport actually depends on polariton formation on these hybrid quasi-particles between light and matter. And now something that we did in collaboration with the FICE group, we look indeed whether they have been looking recently indeed whether these activation gaps actually get modified in the experiments. And some really nice and sort of supporting data that we have in this paper here is the activation temperature of the gaps of the quantum Hall plateaus at 0 coupling. And now you see here that if the coupling is at 20 and 30%, you see that the activation gap is much smaller than the one that you have of the uncoupled system. And this sort of is in qualitative agreement, at least with what we have been seeing from our theory. So, of course, we want to do a little bit more. And now we have been working on trying to see how well this experimental finding matches with theory. So we want to look for for a better quantitative agreement of reproducing exactly these suppression of the thermal activation gaps. And something which is also very interesting and we want to do is to get some actual real theory of what is the effect of the polariton lifetimes for this quantum Hall transport, because what I showed you so far is just I use as a tuning parameter, as a phenomenological parameter in this of the broadening in the Kubo formalism. So these are a couple of outlooks that we are trying to pursue. So coming now to the second part of my talk, and I hope I have time, or this is your work, so you're ITAMP director. I can take more time. So, yes, okay. So this is a collaboration that we'll see. Okay, it should be enough. I'll go fast. So this is a collaboration with Hossein and Simos, and we're trying now to look into like ultra cold systems. At least for me, that was new to jump into this kind of systems. So For the motivation for us was this polaritonic chemistry. Of course, this is extremely complicated because these are very large ensembles of molecules in solvation and so on and so forth. And these are organic molecules. But some key experimental signatures that show up is that excited and ground state properties get modified, that somehow chemistry depends on collective coupling, and that you have very large numbers of molecules. This is very unusual for chemistry, which is a local phenomenon, and that there is this very important resonant effect which always show up in these modifications of these chemical reactions. So it only happens when you are in resonance. Of course, this is very difficult, very challenging, and has not been understood. And our idea was, okay, since this is so complicated in terms of temperature, solvation, and so on and so forth, let's motivate ourselves, or let's try to understand how this could be happening with a model motivated from ultra-cold physics, but collectively coupled. Okay. And that's why we looked into ultra-cold ions, which are trapped in a harmonic potential. So again, these guys are charged, and now the cavity, we want to couple it to the motional degrees of freedom. So this is a trapping potential, which gives us this frequency omega. This is the particles again, they are charged, so this is the coupling to the cavity field. This is the single mode, but with both polarizations in this case, and this is a Coulomb interaction. And again, we take the photon field to be homogeneous, and because the system is harmonic, we can run again this center of mass transformation, and what you see again is that the cavity field only couples to the center of mass momentum. So you can do again these transformations and isolate the photon matter processes just in the center of mass frame. So you can again run the Bogolyubov transformation, you can get your polaritons. So I'm going fast since I sort of explained this already. And just keep in mind these two parameters. This is the collective coupling lambda, depends on the particle number or particle density. And this is gamma 2, this is the ratio between cavity and trap frequency. Okay. So now what we would like to look at is what happens in the polariton ground state. Is the polariton ground state interesting at all, or is it a completely trivial state for this collectively large N type of system which is coupled to this single mode? So our polariton ground state is just the vacuum state of the lower and the upper polariton. And first we look into the matter properties. So we take the polariton ground state, we integrate out the photons, and we compute the density profile of the center of mass. And this we can get analytically, and because we're in a harmonic system, we get a Gaussian. But the interesting thing is that we do not have here the bare mass of the system of the particles, but we now acquire an effective mass which depends on the collective coupling and on the ratio between cavity and trap frequency. And now when you plot this effective mass, what you find is that as you increase the coupling, you go from 0.5 to 2. The effective mass as compared to the bare mass, it's increasing, and you go from unity up to 1.5. But the most interesting thing is that when you are at unity, so when gamma 2, when the cavity frequency is in resonance with the trap frequency, this modification, this enhancement of the effective mass of the CM degree of freedom, it actually has this resonance effect. So this made us sort of happy in a sense that this modification, this enhancement of the effective mass, it means that we have a kind of enhancement of localization for the center of mass degree of freedom, and this enhancement of localization exhibits this resonance peak at least. It's not a sharp resonance like in these Ebesen experiments, but it's a sort of broader type of Bell type of resonance. But of course, this is just for the center of mass, and we want to understand what it means, this phenomenon, for the single particle frame and the actual many-body system. Okay? And for that, we followed this sort of effective approach. So essentially, the center of mass system experiences without the cavity such a trapping potential. And now, since the bare mass went into this effective one, it means that the trapping potential that the center of mass field has been renormalized. And if you subtract the effective from the effective mass the bare one, then you essentially obtain what is the cavity-mediated potential for the center of mass. And if you go back now into the single particle frame, into the lab frame, you see that you have this single particle contribution. This is a renormalization of the single particle trapping potential, and you have this all-to-all long-range interactions. And then what Simos did, he took these cavity-induced interactions, plugged them into his ab initio code, and then we want to see how these change the actual many-body density. So in order to understand what happens, he took a simple model of 1D bosons. We completely neglected the Coulomb interaction in order to see what is the effect of these cavity-induced interactions. And now here on the left, I'm showing you the difference of the many-body density of the coupled minus the uncoupled system. And here Simos did this calculation, so I should not claim any type of, yes, he did it. So yeah, I should not claim anything for that, except, and we went from 20 up to 10,000 particles. For small particle numbers, he checked it also with MCTDH. And for such particle numbers, we had to go into the mean field. And then what you see here is that on the sides of the trap, you are losing density because of the coupling, but at the center of the trap, you are gaining density. So what this means is that the particles are coming together, so these forces are essentially attractive, and you're essentially, the whole ionic cloud is localizing. So this corroborates what we saw in the center of mass, but at the many-body level, that there is indeed this enhancement of localization. And now, if you look at the peak, so at the center of the trap, at the peak of how this peak is scaling with the particle number and for different couplings, what you see is that as you go from strong to ultra strong, there is a transition from a type of linear increase of this peak here. It goes from linear to a square root n type of behavior. And of course, the effect in this square root n regime is also much larger, the deviation. So what these two plots tells you that there is an enhancement of localization in the many-body density, and that there is this collective behavior, decay-like in a sense that is a non-linear type of increase of this peak. And the last thing I will try to talk about very quickly, so in the interest of time, is then what happens on the photonic side. Because now, up to here, I only told you about the matter, but now we want to look whether also photonically this polarity on ground state is interesting. And for that, we look into photon occupations and photon correlations as imprinted by the Mundell Q parameter. And what we find is that as a function of the collective coupling, the photon population in the ground state, it is non-zero. And once the coupling is at the order of 1, you also have essentially one photon being shared within the whole ionic cloud. And also, if you compute the Mundell Q parameter, you find it to be positive. And what these two plots convey is that essentially in the polarity on ground state, you have bunching on photons, because the Mundell Q parameter is positive, so you have super Poissonian statistics, so you have these correlated bunch photons in the ground state. So also on the photon side, this polaritonic ground state is also non-trivial. And one question which is very interesting is whether can we get anti-bunching, which would mean that we have some non-classical correlations in the system. And this is something that we are now doing with Ilya Tutunikov, that he very recently joined ITAMP. And this is ongoing work, but I will just show you one plot, since I have bothered you with already too much. So what we're doing now, we take this collectively coupled system of ions in the harmonic trap, and we inject a coherent state of photons. So we initiate the system, the cavity system, from a coherent state, and now we looked into the dynamical evolution of the Mundell Q parameter when you are out of resonance, in resonance, and again out of resonance. And now what you see is that you start at t equals 0 from positively correlated, so super bunched photons, but as you let time evolve, you see here that you also end up having this anti-bunch, non-classical quantum correlated photons. And this is here, the orange and blue line is for different kind of coherent state preparation, whether the coherent shift is real or imaginary. So what this tells you is that this sort of, this little system essentially works in principle as a generator of which takes coherent photons and translates them into non-classical anti-bunched photons. And of course, now there is more to be done on this. We also want to look what is the effect of dissipation on how these anti-bunched photons still survive and so on and so forth. But this is already very exciting for us. And let me just end by saying happy birthday to ITAMP and contribute with a memory from 2 years ago where we climbed up with Simos, Hossein, and Matteo Magoni, who was a visitor here. We climbed up on Mount Monadnock. It's one of my most favorite memories here at ITAMP. And with this, I want to thank you all for your attention.
Questions for Vasilis?
Thank you so much. I have to say I resonate with the comment that you shouldn't take the single mode approximation, but I'm not going to ask about that. Instead, I'm going to ask about disorder.
Yes.
So in terms of the quantum Hall regime,
Yes.
what I understood from what you were saying is that the dominant effect that you're predicting is effectively a reduction of the temperature at which topological stability occurs. And this reduction is driven by the gap dynamics. Have you explored how the coupling to the cavity changes the effects of disorder on the width of the plateaus?
No, we have not included disorder at all. I mean, disorder makes things very complicated in the sense that it breaks this separation between center of mass motion and interparticle correlations, so it just makes exponentially difficult this to model essentially. So, and I mean, Cristiano Ciuti has a paper on PRB which is trying to do that, and what he sees is that because of disorder, you can essentially sort of correlate the one edge of the sample to the other, and somehow that this correlation mechanism survives. But from that, you cannot get any actual type of prediction about how should these plateaus be modified. But there is this only one work when you can see this sort of non-local connection of the edges, and this is something that would also evade the topological protection. But then it's very difficult to get any actual prediction for the transport, because it's just an n-body disorder collectively coupled system, and you are just... Yes.
Other questions?
So I didn't understand in the second part. I mean, you started with a decoupled center of mass mode, but then suddenly you could change the crystal structure, which so if you let's say if you say you change the density, so this means you
They dope the system.
Sorry.
You can change the density by dope.
Now in the last part. You said that in the second part.
In the second part.
So you.
This is in a harmonic trap.
Yeah, and then the center of mass should completely decouple.
Yes.
But somehow you still got an effect on the many-body density, or what do you call it?
Yes. So this is the density of the system. So essentially, what this shows is, so this is the difference of the coupled density from the uncoupled one, right? And what this tells you is how the many-body density has changed because of these cavity-mediated interactions.
But does it mean now you get a difference in the distance in the Wigner crystal between the ion, or just that the center of mass is...
Just the center of mass essentially modified, but the effect survives in the full many-body density. But there is no crystal here, so if you have a crystal, it's very different. You won't even have this separation essentially between the center of mass and interparticle correlations.
So these are independent ions then, or
yes, these are floating particles, if you wish.
And just and the lambda here with this parameter, is this kind of coupling over omega, or how do you define it?
Yes, let me go back to that. I went a bit fast. I'm sorry. So essentially, this is like the particles in the divided by the area of the mirrors, and then also by the trap frequency. So it's just a...
So lambda equal 1 means collective coupling is equal to the cavity frequency. Is that right?
Well, no.
No.
No, the gamma, so this is the ratio defines the ratio between cavity and trap, and this is the collective coupling. So lambda equals 1 would mean that the vacuum Rabi splitting is at the order of 1. Does this make sense? The vacuum Rabi splitting is...
Okay, so but now that I don't understand the difference between lambda and gamma 2, or?
I mean, this is cavity frequency, this is trap frequency, and this is particle density, and also just normalized with trap frequency. It's just a collection of parameters. It's nothing really...
Okay, yeah.
We can talk about it. There is something that confuses you particularly.
Okay, thank you.
Sharon?
So it's actually a question about this last part as well, kind of following up this previous question. So this is, as I'm understanding, this is actually, there is no spatial part to this system, right? It's like, because it couples to center of mass and relative motion, and that's, I guess, similar to the fact that there's no crystal. So in that sense, it's not really many-body. And because you are also showing like
I'm saying what, I mean, we agree that the many body density is like the average density of all the particles.
it's like mean field, I mean, in that sense, mean field of a...
Yeah, this was mean field computations, but the many body, so the overall density is a many body observable. That's what I mean.
Okay, yeah, observable, yeah.
It's a many body observable.
But you are taking out the spatial part, basically. So there is no, like, you know, a lattice or something.
There's no lattice, it's just in a trap.
In that sense, it is actually like, it's just really the MFT, mean field limit
It's a mean
of
field
many.
phenomenon. It's a mean
Yeah.
field phenomenon. I'm not saying it's a strongly correlated or something. It's a mean field phenomenon.
Okay.
Any more? Going once, going twice. Okay, then join me in thanking Vasilis, Johannes, and Eugene. We come to the end of the scientific sessions, but not the end of the symposium. So there is a fellows dinner. I'm not invited. No, somebody told me, which is by invitation, which is later tonight. And then, even more importantly, there's a soccer match tomorrow. Some of the fellows will play, and the other fellows will be the cheerleaders. So, without further ado, thank you very much for coming, and well, this is for you. So, see you in, well, later tonight.